Momentum, MV. Define momentum. Define impulses and describe how it affects changes in momentum. Explain why an impulse is greater when an object bounces than when the same object comes to a sudden stop. State the law of conservation of momentum. Describe how the conservation of momentum applies to collisions. Describe how the vector nature of momentum affects the law of conservation of momentum. The big idea: momentum is conserved for all collisions as long as external forces don't interfere. Have you ever wondered how a Taekwondo expert can break a stack of cement bricks with the blow of a bare hand, or why falling on a wooden floor hurts less than falling on a cement floor, or why follow-through is important in golf, baseball, and boxing? To understand these things, you need to recall the concept of inertia, introduced and developed when we discussed Newton's laws of motion. Inertia was discussed both in terms of objects at rest and objects in motion. In this chapter, we are concerned only with the concept of inertia in motion, momentum. Discover: how does a collision affect the motion of marbles? 1. Place 5 marbles all identical in size and shape in the center groove of a ruler. Launch a 6th marble toward the 5 stationary marbles. Note any change in the marble's motion. 2. Now launch 2 marbles at 4 stationary marbles. Then launch 3 marbles at 3 stationary marbles, and so on. Note any changes in the marble's motion. 3. Remove all but 2 marbles from the groove. Roll these 2 marbles at each other with equal speeds. Note any changes in the marble's motion. Analyze and conclude. 1. Observing: how did the approximate speed of the marbles before each collision compare to after each collision? 2. Drawing conclusions: what factors determine how the speeds of the marbles changes in a collision? Predicting: what do you think would happen if 3 marbles rolling to the right and 2 marbles rolling to the left with the same speed were to collide? Momentum 8.1. We know that it's harder to stop a large truck than a small car when both are moving at the same speed. We say the truck has more momentum than the car. By momentum, we mean inertia in motion. More specifically, momentum is the mass of the object multiplied by its velocity. Momentum equals mass times velocity, or in abbreviated notation, momentum equals mv. Can you think of a case where the roller skate and the truck shown in 8.1 would have the same momentum? Well, here is a shot of 8.1. A truck rolling down a hill has more momentum than the roller skate with the same speed. But if the truck is at rest and the roller skate moves, then the skate has more momentum. The roller skate and the truck have the same momentum if the speed of the roller skate is much greater than the speed of the truck. How much greater? As many times greater as the truck's mass is greater than the roller skate's mass. Get it? For example, a 1,000 kilogram truck backing out of a driveway at 0.01 meters per second has the same momentum as a 1 kilogram skate going 10 meters per second. Both have a momentum of 10 kilogram meters per second. When direction is not an important factor, we can say momentum equals mass times speed, which is still abbreviated mv. A moving object can have a large momentum if it has a large mass, a high speed, or both. A moving truck has more momentum than a car moving at the same speed because a truck has more mass. But a fast car can have more momentum than a slow truck, and a truck at rest has no momentum at all. Figure 8.1 compares the momentum of a truck to that of a roller skate. Here is figure 8.1 for your perusal again. What factors affect an object's momentum? What factors affect an object's momentum? 8.2, impulse changes momentum. If the momentum of an object changes, either the mass or the velocity or both change. If the mass remains unchanged, as is most often the case, then the velocity changes and acceleration occurs. What produces acceleration? We know the answer is force. The greater the force acting on an object, the greater its change in velocity, and hence the greater its change in momentum. Notes: the derivation of F delta T equals delta mv is given in Appendix G, note 8.2. Impulse. The change in momentum depends on the force that acts and the length of time it acts. As figure 8.2 shows, apply a brief force to a stalled automobile and you produce a change in its momentum. Apply the same force over an extended period of time and you produce a greater change in the automobile's momentum. A force sustained for a long time produces more change in momentum than does the same force applied briefly. So both force and time are important in changing an object's momentum. Figure 8.2. When you push with the same force for twice the time, you impart twice the impulse and produce twice the change in momentum. The quantity force times delta time interval is called impulse. In shorthand notation, impulse equals F delta T. The greater the impulse exerted on something, the greater will be the change in momentum. The exact relationship is impulse equals change in momentum. F delta T equals delta mv. Bungee jumping, physics of sports. The impulse-momentum relationship is put to a thrilling test during bungee jumping. Be glad the rubber cord stretches when the jumper's fall is brought to a halt, because the cord has to apply an impulse equal to the jumper's momentum in order to stop the jumper, hopefully above ground level. Note how F delta T equals delta mv applies here. The momentum mv we wish to change is the amount gained before the cord begins to stretch. F delta T is the impulse the cord supplies to reduce the momentum to zero. Because the rubber cord stretches for a long time, the large time interval delta T ensures that a small average force acts on the jumper. Elastic cords typically stretch to twice their original length during the fall. The impulse-momentum relationship helps us to analyze a variety of situations where the momentum changes. Consider the familiar example of impulse in the following cases of increasing and decreasing momentum. Increasing momentum. To increase momentum of an object, it makes sense to apply the greatest force possible for as long as possible. A golfer teeing off and a baseball player trying for a home run do both of these things when they swing as hard as possible and follow through with their swing. The forces involved in impulses usually vary from instant to instant. Look at figure 8.3. Figure 8.3, the force of impact of a golf ball varies throughout the duration of the impact. A golf club that strikes a golf ball exerts zero force on the ball until it comes into contact with it. Then the force increases rapidly as the ball becomes distorted. The force then diminishes as the ball comes up to speed and returns to its original shape. When we speak of such forces in this chapter, we mean the average force, decreasing momentum. If you were in a car that was out of control and had to choose between hitting a haystack, as in figure 8.4, or a concrete wall, as in figure 8.5, you wouldn't have to call on your knowledge of physics to make up your mind. Common sense tells you to choose the haystack. Figure 8.4, if the change in momentum occurs over a long time, the force of impact is small. You can see it's large V, small m, large T, small f. The change in the momentum is going to equal the impulse. 8.5, if the change in momentum occurs over a short period of time, the force of impact is large. When a dish falls, will the impulse be less if it lands on a carpet or if it lands on a hard floor? No, the impulse would be the same for either surface because the same momentum change occurs for each. It is the force that is less for the impulse on the carpet because the greater the time of the momentum change. Let's look at two notes. Whether body A acts on body B or body B acts on body A, in accordance with Newton's third law, both have the same amount of impulse, F delta T. And a flower pot dropped onto your head bounces quickly. Ouch. If bouncing took a longer time, as with a safety net, then the force of the bounce would be much smaller. All right, back to the haystack. But knowing the physics helps you to understand why hitting a soft object is entirely different from hitting a hard one. In the case of hitting either the wall or the haystack and coming to a stop, your momentum is decreased by the same impulse. The same impulse does not mean the same amount of force or the same amount of time. Rather, it means the same product of the force and time. By hitting the haystack instead of the wall, you extend the contact time, the time during which your momentum is brought to zero. A longer contact time reduces the force and decreases the resulting deceleration. For example, if the time is extended 100 times, the force of impact is reduced 100 times. Whenever we wish the force to be small, we extend the time. We know that a padded dashboard in a car is safer than a rigid metal one and that airbags save lives. You also know that to catch a fast-moving ball safely with your bare hands, you extend your hand forward so there's plenty of room for it to move backward after making contact with the ball. When you extend the time of contact, you reduce the force of the catch. When jumping from an elevated position down to the ground, you should bend your knees when your feet make contact with the ground. By doing so, you extend the time during which your momentum decreases by 10 to 20 times that of a stiff leg abrupt landing. The resulting force on your bones is reduced by 10 to 20 times. If the boxer in figure 8.6 is able to make contact time 5 times longer by riding with the punch, how much will the force of the punch impact be reduced? Since the time of impact increases 5 times, the force of impact will be reduced 5 times. A wrestler thrown to the floor tries to extend his time of hitting the mat by extending his muscles and spreading the impulse into a series of smaller ones as his foot, knee, hip, ribs, and shoulder successively hit the mat. Of course, falling on a mat is preferably to falling on a solid floor because the mat also increases the stopping time. When a boxer gets punched, the impulse provided by the boxer's jaw must counteract the momentum of the punch. As figure 8.6a shows, when a boxer moves away from the punch, he increases the time contact and reduces the force. When the boxer moves toward the punch, as in figure 8.6b, the time of contact is reduced and the force is increased. All right, here's the boxer, figure 8.6. The impulse provided by a boxer's jaw counteracts the momentum of the punch. A, the boxer moves away from the punch. And B, the boxer moves towards the punch. We know a glass dish is more likely to survive if it is dropped on a carpet rather than on the sidewalk because the carpet has more give than the sidewalk. Ask why a surface with more give makes for a safer fall, and you will get a puzzled response from most people. They may simply say, because it gives more. However, your question is, why is a surface with more give safer for dishes? In this case, a common explanation isn't enough. A deeper explanation is needed. To bring the dish or its fragments to rest, the carpet or the sidewalk must provide an impulse, which you know involves two variables, force and time. Since time is longer hitting the carpet than hitting the sidewalk, the smaller force results. The shorter time hitting the sidewalk results in a greater stopping force. The safety net used by circus acrobats is a common example of how to achieve the impulse needed for a safe landing. The safety net reduces the stopping force on a fallen acrobat by substantially increasing the time interval of the contact. Sometimes a difference in time is important, even if you can't notice the give in a surface. For example, a wooden floor and a concrete floor may both seem rigid, but the wooden floor can have enough give to make quite a difference in the forces that these two surfaces exert. Concept check. What factors affect how much an object's momentum changes? 8.3, bouncing. If a flower pot falls from a shelf onto your head, you may be in trouble. If it bounces from your head, you may be in more serious trouble. Why? Because impulses are greater when an object bounces. The impulse required to bring an object to a stop and then to bring it back again is greater than the impulse required merely to bring the object to a stop. Suppose, for example, you catch the falling pot with your hands. You provide an impulse to reduce its momentum to zero. If you throw the pot upward again, you have to provide additional impulse. It takes a greater impulse to catch the pot and throw it back up than merely to catch it. This increased amount of impulse is supplied to your head if the pot bounces from it. The karate expert in figure 8.7 strikes the bricks in such a way that her hand is made to bounce back, yielding as much as twice the impulse to the bricks. The fact that impulses are greater when bouncing takes place was used with great success during the California gold rush. The water wheels used in gold mining operations were not very effective. A man named Lester A. Pelton saw that problem had to do with the flat paddles on the water wheel. Here is figure 8.7. Someone imparts a large impulse to the boards in a short time and produces considerable force. He designed the curved-shaped paddle that is shown in figure 8.8. This paddle caused the incoming water to make a U-turn upon impact with the paddle. Because the water bounced, the impulse exerted on the water wheel increased. Pelton patented his idea and probably made more money from his invention, the Pelton wheel, than any of the gold miners earned. Physics can indeed make you rich. How does the impulse of a bounce compare to stopping only? Figure 8.8. The curved blades of the Pelton wheel cause water to bounce and make a U-turn, producing a large impulse that turns the wheel. 8.4 Conservation of momentum. Consider the cannon fired in figure 8.10. The force on the cannonball inside the cannon barrel is equal and opposite to the force causing the cannon to recoil. Recall Newton's third law about action-reaction forces. These forces are internal to the system comprising of the cannon and the cannonball, so they don't change the momentum of the cannonball system. Before the firing, the system is at rest and the momentum is zero. After the firing, the net momentum or total momentum is still zero. Net momentum is neither gained nor lost. Let's consider the effects of internal and external forces carefully. 8.9 Teacher shows that a block topples when the swinging dart bounces from it. When he removes the rubber head of the dart so it doesn't bounce when it hits the block, no toppling occurs. Figure 8.10. The momentum before firing is zero. After firing, the net momentum is still zero because the momentum of the cannon is equal and opposite to the momentum of the cannonball. It is a vector quantity like velocity and force. Momentum can be canceled. So, although the cannonball in the preceding example gains momentum when fired and the recoiling cannon gains momentum in the opposite direction, the cannonball system gains none. The momenta, plural for momentum, of the cannonball and cannon are equal in magnitude and opposite in direction. Note, most of the cannonball's momentum is in speed. Most of the recoiling cannon's momentum is in mass. So, mv equals mv. Therefore, these momenta cancel each other out for the system as a whole. No external force acted on the system before or during firing, so no net force acts on the system. There is no net impulse on the system, and there is no net change in the momentum. In every case, the momentum of a system cannot change unless it is acted on by external forces. Note, a conservation law is constancy during change. Conservation laws are a source of deep insight into the simple regularity of nature and are often considered the most fundamental of physical laws. Newton's second law states that if no net force is exerted on a system, no acceleration occurs. Does it follow that no change in momentum occurs? Yes, because no acceleration means no change occurs in velocity or in momentum, mass times velocity. Another line of reasoning is simply that no net force means there is no net impulse and thus no change in momentum. A system will have the same momentum before some internal interaction as it has after the interaction occurs. When momentum, or any quantity in physics, does not change, we say it's conserved. The law of conservation of momentum describes the momentum of a system. The law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged. If a system undergoes changes wherein all forces are internal, as for example in atomic nuclei undergoing radioactive decay, cars colliding, or stars exploding, the net momentum of a system before and after the event is the same. What does the law of conservation of momentum state? 8.5 Collisions. The collision of an object clearly shows the conservation of momentum. Whenever objects collide in the absence of external forces, the net momentum of both objects before the collision equals the net momentum of both objects after the collision. Net momentum before collision equals net momentum after collision. Elastic collisions. When a moving billiard ball collides head-on with a ball at rest, the first ball comes to rest and the second ball moves away with a velocity equal to the initial velocity of the first ball. We see that momentum is transferred from the first ball to the second ball. When objects collide without being permanently deformed and without generating heat, the collision is said to be an elastic collision. Colliding objects bounce perfectly in perfect elastic collisions, as shown in figure 8.11. Note that the sum of the momentum vectors is the same before and after each collision. Inelastic collisions. A collision in which the colliding objects become distorted and generate heat during the collision is an inelastic collision. Momentum conservation holds true even in inelastic collisions. Whenever colliding objects become tangled or coupled together, a total inelastic collision occurs. The freight train cars in figure 8.12 provide an example. Figure 8.11. Colliding objects bounce perfectly in elastic collisions. A moving ball strikes a ball at rest. B, two moving balls collide head-on. And C, two balls moving in the same direction collide. Remember, conservation of momentum. Figure 8.12. In an inelastic collision between two freight cars, the momentum of the freight car on the left is shared with the freight car on the right. This is a very important example. Study this very carefully. Suppose the freight cars are of equal mass m and that one car moves at 4 meters per second towards the other car that is at rest. Can you predict the velocity of the coupled cars after impact? From the conservation of momentum, net momentum before collision equals net momentum after collision, or in the equation form, shown here, since twice as much mass is moving after the collision, can you see that the velocity, v after, must be half of 4 meters per second? Solving for the velocity after the collision, we find v after equals 2 meters per second in the same direction as the velocity before the collision, v after. The initial momentum is shared by both cars without loss or gain. Momentum is conserved. Most collisions usually involve some external force. Billiard balls do not continue indefinitely with the momentum imparted to them. The moving balls encounter friction with the table and the air. These external forces are usually negligible during the collision, so the net momentum does not change during collision. The net momentum of two colliding trucks is the same before and just after the collision. As the combined wreck slides along the pavement, friction provides an impulse to decrease its momentum. Similarly, a pair of space vehicles docking in orbit have the same net momentum just before and just after contact, since there is no air resistance in space, the combined momentum of the space vehicles after docking is then changed only by gravity. Perfectly elastic collisions are not common in everyday world. We find in practice that some heat is generated during collisions. Drop a ball, and after it bounces from the floor, both the ball and the floor are a bit warmer. Even a dropped super ball will not bounce to its initial height. At microscopic level, however, perfectly elastic collisions are commonplace. Momentum is conserved for all collisions, elastic and inelastic, when there are no external forces to provide net impulse. For example, electrically charged particles bounce off one another without generating heat. They don't even touch in the classic sense of the word. Later chapters will show that the concept of touching needs to be considered differently at the atomic level. How does conservation of momentum apply to collisions? Pucks and carts ride nearly free of friction on cushions of air, on air tracks, like the one shown in figure 8.13. Galileo worked hard to produce smooth surfaces to minimize friction. How he would have loved to experiment with today's air tracks. Think, suppose one of the gliders in figure 8.13 is loaded so it has 3 times the mass of the other glider. The loaded glider is initially at rest. The unloaded glider collides with the loaded glider and the two gliders stick together. Describe the motion of the gliders after the collision. The mass of the stuck together gliders is 4 times that of the unloaded glider. Thus, the post collision velocity of the stuck together glider is 1/4 of the unloaded glider's velocity before collision. The velocity is in the same direction as before, since the direction as well as the amount of momentum is conserved. 8.13. An air track nicely demonstrates conservation of momentum. Many small air jets provide a nearly frictionless cushion of air for the gliders to go on. And here is an additional illustration that shows collisions on an air track. Do the math. Consider a 6-kilogram fish that swims toward and swallows a 2-kilogram fish that is at rest. If the larger fish swims at 1 meter per second, what is its velocity immediately after lunch? Momentum is conserved from the instant before lunch until the instant after. In so brief an interval, water resistance does not have time to change the momentum. So we can write net momentum before lunch equals net momentum after lunch. Reducing the equation, net mv before lunch equals net mv after lunch. All right, as we continue, we're going to plug in now. So we have 6 kilograms times 1 meter per second plus 2 kilograms times 0, and then 6 plus 2 times the velocity after. So we're going to reduce it to 3/4 meter per second velocity after for the system. We see that the small fish has no momentum before lunch because its velocity is 0. Using simple algebra, we see that after lunch, the combined mass of the two fish system is 8 kilograms, and its speed is 3/4 meter per second in the same direction as the large fish's direction before lunch. Suppose the small fish is not at rest, but is swimming towards the larger fish at 2 meters per second. What is the velocity of the large fish immediately after lunch? We see that the small fish has no momentum before lunch because its velocity is 0. Using simple algebra, we see that after lunch, the combined mass of the two fish system is 8 kilograms, and its speed is 3/4 meters per second, in the same direction as the large fish's direction before lunch. So we say net MV before lunch equals net MV after lunch. And then we're going to plug in the values. Notice -2 meters per second for the smaller fish, because that's the direction it's going. It's going in the opposite direction of the larger fish. And then we solve for V after. The system, 6 plus 2 after. Then we have the value is going to reduce even more. And so it's going to be 6 minus 4 equals 8V, essentially. And then solving for V after. Rearranging further, taking our time, we see it's going to be 1/4 meters per second, the velocity after. You got to take your time and make sure that everything is done properly. The negative momentum of the small fish is very effective in slowing the large fish. If the small fish were swimming at -3 meters per second, then both fish would have equal and opposite momenta. Zero momentum before lunch would equal zero momentum after lunch, and both fish would come to a halt. More interestingly, suppose the small fish swims at -4 meters per second. So you put that in the values. Notice the -4 is in the equation, and that's going to be times 2, and that'll be -8, that term. And then let's go to the next slide. And you'll see that it comes down to -1/4 meters per second. The minus sign tells us that after lunch, the two fish system moves in a direction opposite to the large fish's direction before lunch. 8.6 Momentum Vectors. Momentum is conserved even when interacting objects don't move along the same straight line. To analyze momentum in any direction, we use the vector techniques we've previously learned. The vector sum of the momentum is the same before and after the collision. We'll look at momentum conservation involving angles by briefly considering the three following examples. Notice in figure 8.14 that the momentum of car A is directed east and that of car B is directed north. Figure 8.14. Momentum is a vector quantity. The momentum of the wreck is equal to the vector sum of the momentum of car A and car B before the collision. If their momenta are equal in magnitude after colliding, their combined momentum will be in a northeast direction with a magnitude √2 times the momentum either vehicle had before the collision, just as the diagonal of the square is √2 times the length of a side. Figure 8.15 shows a falling firecracker that explodes into two pieces. The momenta of the fragments combine by vector rules to equal the original momentum of the falling firecracker. 8.16 shows tracks made by subatomic particles in a bubble chamber. The mass of these particles can be computed by applying both the conservation of momentum and the conservation of energy laws. The conservation of energy law will be discussed in the next chapter. 8.15 shows the firecracker bursts. The vector sum of the momenta of its fragments add up to the firecracker's momentum just before bursting. Momentum is conserved for high-speed elementary particles as shown by the tracks they leave in a bubble chamber. The conservation laws are extremely useful to experiments in the atomic and subatomic realms. A very important feature of their usefulness is that forces do not show up in the equations. Forces in collisions, however complicated, are not a concern. Conservation of momentum and, as a next chapter will discuss, conservation of energy are the two most powerful tools of mechanics. Their application yields detailed information that ranges from understanding the interactions of subatomic particles to entire galaxies. What is true about the vector sum of momenta in a collision? Summary: momentum. A moving object can have a large momentum if it has a large mass, a high speed, or both. The change in momentum depends on the force that acts and the length of time it acts. The impulse required to bring an object to a stop and then to throw it back again is greater than the impulse required merely to bring the object to a stop. The law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged. Whenever objects collide in the absence of external forces, the net momentum of both objects before collision equals the net momentum of both objects after collision. The vector sum of the momentum is the same before and after a collision.